universe is not a normal place. According to the current popular model of the universe, normal matter that can be seen or observed accounts for just 5% of the universe. This means the larger part of the universe consists of dark, unseen substances. These unseen and mysterious parts of the universe are known as the dark part of the universe. It could either be dark energy or dark matter. While dark energy makes up a whopping 75% of the universe, dark matter completes the arrangement with a 25% composition. Interestingly, scientists have not been able to figure out what dark matter looks like. However, this is how they concluded that it must exist in some way. You see, after observing all the atoms and light in the universe, scientists realized that there was much more unseen mass. This is simply because all the atoms and light make up about a tiny fraction of its mass. In this case, there was a missing mass that had to be somewhere. So for want of a better name, I called it dark matter. Meanwhile, they also observed that the universe was not static, but was expanding at a steady pace. However, the expansion was not caused by a mysterious, unseen energy. Like the unknown matter, they concluded that this mysterious, unknown energy is dark energy. So what do we know about these two mysterious components of the universe? What are they? How do they behave and affect our daily lives? Join me as we explore the mysteries of the largely unknown part of the universe to uncover the secrets of dark energy and dark matter. But before we embark on the journey, fasten your seatbelts and take a few seconds to like this video and subscribe to the channel, because this journey promises to be as fascinating as it is mysterious. That said, let's kick things off by answering some important questions. Matter. Does it really exist, or is it just another cooked-up fact to explain the unknown? Dark matter is not even a real name. It's a placeholder, just like X and Y in your high school algebra class. It would enjoy a new name when scientists figure out what it really is, but for now, it is what it is. But what do we really know about dark matter? For starters, dark matter is stuff in space that can be felt but cannot be seen. They have gravity and affect things around them, but they are invisible. These sneaky space ghosts are so slick that they are also invisible to electromagnetic radiation. As a result of this, scientists cannot detect them, even with the best sensors. Although scientists cannot see these space ghosts, even with their sophisticated instruments, they have some evidence to prove that dark matter exists. You see, in 1933, a scientist named Fritz Zwicky observed the velocities of galaxies in the Coma cluster, and when he ran the numbers, something was off. The velocities were way higher than what was expected when you added the masses of the individual galaxies. Fritz was puzzled because for those galaxies to move at the velocity he observed, there had to be an extra mass that's much more than the masses of the galaxies combined. So for the first time, Fritz was faced with a huge amount of matter that was technically there, but not there. This was the first evidence that there was matter out there present by observation, but it was invisible to any known equipment. After Fritz, other scientists have stumbled upon dark matter at work. Although none of them caught the ghost, they documented their encounters. This leads us to the next two pieces of evidence, which prove that although we cannot yet see dark matter, it exists in practice. Astronomers observe galaxies and large-scale space structures with gravitational lensing. The data and results from this exercise every single time exceed their expectations. It just shows them that, although they cannot see it, there's something more out there. You see, before Fritz, scientists believed that the universe was made up of baryonic matter, or, simply put, matter that is visible to light. So when scientists ran the results of gravitational lensing, the results blew their minds. After accounting for the baryonic matter, they were astonished to find 5 times more matter in the universe, once again proving the existence of a large number of non-baryonic matter that was felt but unseen. Like Fritz, they discovered dark matter, not by seeing it, but by observing it in action. However, there was still one issue. Scientists are sure there are truckloads of invisible matter in the universe, but they had one problem: finding out exactly how much of it was out there. Recently, with the help of a process called cosmic microwave background radiation, or CMB, they got their answer. With CMB, they discovered that dark matter constituted about 25% of the universe, while baryonic matter made up 5%. Although this observation answered their questions, it opened up more questions that needed answers. For example, if baryonic matter constituted 5% of the universe and dark matter 25%, what made up the remaining 75%? However, the greatest thing they got from this observation was the properties of dark matter. From their observations, this unknown, invisible matter reacts with other matter in only one way: gravity. Remember that dark matter is just like the X and Y from your high school algebra class. So if that is the case, is it possible that dark matter is not really unknown? Over the years, there has been a great deal of speculation as to what dark matter really is. First off, there's a general consensus among scientists that dark matter contains non-baryonic matter. But what kind of baryonic matter is in dark matter? This is likely the key to finding out their true nature. But identifying dark matter has not been straightforward because scientists have several candidates that could likely be the great unknown dark matter. The first of these likely candidates are weakly interactive massive particles, or WIMPs. The discovery that dark matter had weak interactions with other particles pointed several fingers to WIMP. This is because, although WIMPs are up to 100 times heavier than protons, they have a very weak interaction with other particles that makes them as sneaky as dark matter and very difficult to detect. But here's the thing, WIMPs are not the only particles with weak interactions that can go totally undetected. The next suspect is just like it, but slightly different. Just like WIMPs, sterile neutrinos hardly interact with regular matter. These particles just stream from the sun and pass through Earth without really interacting with anything. But unlike WIMPs, sterile neutrinos have one plus that makes them closer to the description of dark matter. They would only interact with regular matter through gravity. But a far more interesting candidate for dark matter are axions, especially because they solve two mysteries surrounding dark matter. First, they give more insight into the nature of dark matter. And second, they solve one major problem with dark matter, the charge polarity problem. Although axions come off strongly as a candidate for dark matter, there is still one hurdle to cross for scientists to proclaim them the undisputed candidate, and that is determining their mass and strength of interaction with other particles. Axions come really close as a potential candidate, but several experiments have ruled it out as a possible candidate for dark matter for two reasons. First off, the mass of an axion is about 100,000 times lighter than that of an electron, which is way too light for a dark matter to look alike. The last nail in the coffin of this possibility is that axions interact with photons in a way that scientists can easily pick up. So with axions out of the way, we are left with just one candidate that might be dark matter. Some scientists suggest that modified gravity is the same as dark matter. According to one of the theories, they suggest that the first scalar field in the superfluid dark matter theory is not just fully dark matter, but also fully a part of space-time. This conclusion is based on two assumptions. The first is that the first scalar field behaves like dark matter fluid on large scales, and secondly, it mediates a force that can modify gravity. Although all of these candidates fit the description in several ways, they still do not tick all the boxes, and as a result, we are still left with the unknowns X and Y. However, this doesn't take away the fact that dark matter is a major part of the universe, especially because it has a hand in its formation. But how does this unseen matter play such a central role in the formation of observable structures? Let's look at it this way. Dark matter is the scaffolding for the universe. This means that the visible parts of the universe collect dark matter to form what we see as stars and galaxies. This is basically how it happens. Several small objects form around dark matter, and it draws them together to form large space structures. Over time, as stars and other space bodies die, they interact with dark matter to produce new bodies that would replace them. Since dark matter plays such a huge role in the formation and continuous functioning of the universe, scientists have not given up on the search for what it really is. As a result, there are several ongoing searches and experiments to uncover the true identity of dark matter. The top three experiments are: 1. The direct detection experiments. Scientists are also working on a second approach, which is an indirect approach that involves the annihilation or decay of certain products. Finally, there are also the particle collider experiments. With these experiments, and more that would follow with the advancement of technology, it is only a matter of time before we figure out the identity of this unseen component of the universe. This is because it is not just another particle in the universe. It has a place in its foundation and continued existence. If dark matter is a mystery that we need to solve to understand the universe, then dark energy is a far deeper mystery, especially because it forms a huge chunk of the universe. What do we know about the mysterious energy that occupies 75% of the universe? And like dark matter, does dark energy even exist? Cosmic objects are held together by strong forces of gravity, and this pull keeps them together. But gravity has an evil counterpart that stretches the fabric of the universe with one goal in mind: to expand the universe, and in the process, it drives these cosmic bodies away from each other. So what is this anti-gravitational force that expands the universe and pulls everything in it apart? We are talking about dark energy. Like dark matter, dark energy is not a real name either. First off, it has far less density than dark matter and even ordinary matter. However, it beats the other two because it is literally everywhere in the universe. Scientists have some strong proof that it really exists. You see, for some time, scientists thought the universe was static. However, after observing dark energy, they suspected that the belief in a static universe was wrong, especially because dark energy was anti-gravity and it did a nice job pulling and stretching the universe. The answer came when some scientists measured a supernova, the type 1a supernova. By observing the supernovae, they discovered that the universe was expanding rapidly. By doing so, they validated the existence of dark energy. Beyond the type 1a supernovae, there are two other measurements of the universe: the baryon acoustic oscillation and the cosmic microwave background radiation, that have proven that it is continuously expanding. So if dark energy exists, what does it look like? There are still a lot of unknowns that make it a theoretical force, and as a result, scientists explain it through theories. The first theory that gives us some insight into how dark energy works is the theory of the cosmological constant. This theory recognizes dark energy as the fundamental energy in space, and upon closer inspection, the theory fits the description, especially in light of Einstein's theory of relativity. According to Einstein's theory, dark energy will have some gravitational qualities and exert a strong influence on the universe. Just like the cosmological constant, the quintessence model also explains dark energy. Quintessence varies with space and time. But bear in mind that this is a theory, and at the end of the day, there's really no evidence supporting its reality, and at the same time, there's none disproving it. As the universe expands, heat and energy will be evenly distributed across the universe. However, due to its increased size, it would be spread thinly so that there is no concentration of heat at any point. As a result, the temperature of the entire universe will fall to a little above absolute zero, a condition known as the Big Freeze. But there's nothing to worry about for now because it would take us about 1 trillion years to get there. Now, we have unpacked all we know so far about these two mysteries of the universe. For sure, they exist, but although we know a thing or two about how they work, there's still a whole lot to learn about them. That said, dark matter and dark energy still remain one of the greatest mysteries out there. So, stay curious and engaged with scientific advancements because the key to understanding the universe might be closer than you think. If you enjoyed this video, please like, comment, and subscribe to help us reach 500 subscribers. I appreciate your support.